When you run pip install, you trust the package. When you pull a Docker image, you trust the registry. It's just what we do. But what about that AI model you just downloaded? Today, we're diving deep into a massive hidden danger, a Trojan horse lurking inside the machine learning models we're all starting to use every single day.
So let's just start with a number that should really get your attention, $6.8 million. According to security researchers, that's the average cost of a single AI supply chain attack. Yeah, this isn't some theoretical what-if scenario. It is a multi-million-dollar problem right now.
And this slide really shows you why. There's this huge disconnect at the very heart of AI development. On one hand, you've got a staggering 78% of organizations relying on third-party models. But on the other hand, 63% of those exact components have known vulnerabilities. We are literally building our AI future on a foundation that has some really serious cracks in it. And that right there brings us to the central question of this entire thing. In an ecosystem where we're constantly sharing and reusing and building on top of each other's models, how do we actually verify trust? I mean, who is really checking the code inside the model? Okay, so this isn't just about a single bug. It's way bigger than that. It's a fundamental trust problem that's baked right into the AI supply chain. The very system that lets us innovate so fast, sharing our work, has also created the absolute perfect opportunity for attackers to strike. So the key idea here is this concept of blind trust. See, developers, data scientists, all of us, we pull these pre-trained models from huge public hubs, and we just kind of assume they're safe. We trust the uploader, we trust the platform, but that trust, a lot of the time it's totally unverified. And just to give you an idea of the scale we're talking about, look at this number, over 500,000 models. And that's just from one platform, Hugging Face, way back in 2023. It's way bigger now. Every single one of those is a potential entry point for an attacker. It creates this massive, almost incomprehensible attack surface. And attackers have a ton of options. They can poison the training data, they can embed these sneaky backdoors that only activate on specific triggers, exploit vulnerabilities in frameworks like TensorFlow or PyTorch, or, and this is what we're going to focus on, they can inject malicious code directly into the model file itself. All right, now let's get into the nitty-gritty, the technical core of how this all works. It really all comes down to a kind of poison pill that's hidden inside a process that most of us as developers just completely take for granted. So to get the vulnerability, you first have to get serialization. It's really just the process of taking a complex object, like a trained AI model that's living in your computer's memory, and turning it into a flat file that you can save or send to somebody else. And here, right here, is where the problem starts. See, the most common way to do this in the Python world is a format called pickle, and super popular frameworks like PyTorch use it by default. So when you run that common torch.load command, what you're actually doing under the hood is deserializing or unpickling that file. This quote just says it all perfectly. The fundamental design of Pickle isn't just to store data, it's also to describe how to reconstruct the object, and that reconstruction process can include executing code. So if you unpickle data from an attacker, you're essentially just handing them the keys and letting them run code on your machine. Okay, so here's the attack broken down. First, an attacker crafts a custom Python object. They then mess with the special method called _reduce. Think of _reduce as the instruction manual for how the unpickler should rebuild the object. But instead of a normal function, they point it to a system command, like one that opens a reverse shell, which gives them remote control. So when your code loads the model, the unpickler just follows these malicious instructions and runs the command. And it's game over. Now, this isn't just theory. Not at all. Let's look at how this exact vulnerability is being actively exploited out there in the wild, basically poisoning the well of open source AI. Researchers have found dozens of these malicious models on public hubs like Hugging Face, and these weren't subtle either. They had payloads designed to establish reverse shells for remote access, to steal credentials, and to connect the victim's machine to attacker-controlled command and control servers. Attackers are getting really clever. One pretty sophisticated method is called model namespace reuse. So they find these popular models in projects that point to a user who has since deleted their Hugging Face account. The attacker then just registers that exact same username, uploads a poison model with the same name, and voila, anyone who pulls the model from the original project now gets the malicious version. And the blast radius for something like this is huge.
This namespace reuse attack has been shown to work against major enterprise platforms like Google's Vertex AI and Microsoft's Azure AI Foundry, because they integrate directly with these public hubs. Basically, any system that's set up to automatically pull the latest version of a model is totally at risk. And this real-world demo shows you just how devastating this can be. A researcher took over a model and embedded a C2, a command and control payload, which lets them operate it remotely. When some unsuspecting employee loaded that model, the researcher gained full control of their machine from all the way across the internet. And of course, attackers know about security scanners, so they're evolving. They've found ways to hide malicious pickle files inside a model's zip archive just by using weird file extensions. The scanner, which is only looking for .pkl files, completely misses it. But PyTorch's loader, well, it's a bit more forgiving, and it'll still find and execute that malicious file. Okay, that is the problem, and it's a big one. But now, let's pivot to the solution. How do we actually build defenses against this stuff? Well, the community's answer is a fundamentally safer file format. So it all comes down to the design philosophy. On the left, you've got Pickle. It's designed for flexibility, which means it can serialize and execute code. On the right, you have Safe Tensors, which was designed purely for security. It is fundamentally incapable of executing code. Why? Because it's only built to store one thing, the numerical data, the tensors that make up the model. That's it. And the advantages go way beyond just security. Because it's a simpler format, it actually enables some cool performance tricks like memory mapping for faster zero-copy loading. It's framework agnostic, so it works across the entire ecosystem, PyTorch, TensorFlow, JAX, you name it. And it supports lazy loading, which is an absolute lifesaver when you're dealing with those massive 100 billion parameter models and you only need a piece of it. But even with all those benefits, this slide shows that adoption is still very much a work in progress. As of early 2025, only about 42% of models on Hugging Face were using the safer format. That means the majority, a full 58%, are still using formats that could be vulnerable. It's often just inertia, legacy code bases, old habits, or just a lack of awareness. But it means the danger is still very much out there. So what can you actually do about it? First, always prefer safe tensors. If you have to use an older model, don't just pull the latest version. Pin it to a specific trusted commit hash. For your mission-critical models, don't even rely on a public hub. Clone it to your own controlled storage. And finally, use static analysis tools to scan your own code for insecure patterns like torch.load. So, we'll end on this thought. The AI you're building is only as secure as the absolute weakest link in its supply chain. It's a chain that's built on trust, but as we've just seen, that trust has to be constantly verified. So, the question is, have you checked every single link?